So now let's talk about the bulk loading of B+ trees. Suppose we want to build an index on a really large table entirely from scratch. How should we do it? Would it actually be efficient if we actually insert each of the tuples one at a time repeatedly until we are done? The answer is no, but why not? Well, if we really ended up doing that, what we ended up doing is we will be navigating from the root of the tree for every tuple that we try to insert, all the way down to the leaf level. And during this process, we'll be modifying a lot of random pages that correspond to the internal part of the tree and also the leaf page for which the new tuple is going to reside. And not being able to reuse the pages that we bring into memory is going to lead to poor cache efficiency. Furthermore, doing this will also leave the leaf pages to be poorly utilized. Some of the leaf pages will end up being really empty, some of them might be half empty, some of them might actually be filled all the way up to the fill factor. So that's bad. Can we do better? Well, what if we actually sort the records before we actually do the insertion? For now, don't worry about the exact algorithm that we will use to do the sorting. Later on in the semester, we're actually going to learn a really good disk-based sorting algorithm for doing exactly that. But if we can do that, then that's great, because rather than navigating from the root of the tree for every tuple, we can actually fill up the leaf pages directly up to the fill factor that we have decided, in this case 3/4. We will update the parent node for each of these new leaf pages that we create up until the point for which the parent node no longer has a space for a new pointer. What do we do then? We do the standard procedure for B+ tree insertion, namely, we promote one of the parent pointers as a new parent and we create a new sibling page. In this case, since the order of the tree is 2, so therefore we promote the first D+1 key, namely 10, to be the new parent of these two new sibling pages that we created. Notice in this case that we'll never be touching the left-hand side of the tree ever again. Why? Because we are basically bulk loading from the right-hand side by inserting new tuples via filling out new leaf pages. So therefore, we never need to touch the left-hand side of the tree again. And furthermore, because we are following the standard procedure for B+ tree insertion, we're actually maintaining all the invariants regarding the fill factor for the leaf pages and the order of the tree for the internal pages, except for the root. We'll basically keep doing this by creating new leaf pages on the right-hand side until we are done. And this procedure has a number of benefits. First of all, we'll be able to use cache much better. For example, the internal sibling node that I'm highlighting here in circle is now able to reside in the cache for most of the time as we are trying to create these new leaf pages on the right-hand side. And furthermore, we'll be ended up in a case where all the leaf pages will be laid out sequentially on the disk, just because of the ordering for which we insert creating these leaf pages one at a time. And that has a lot of benefits later on, as we'll see, for query processing. So in summary, in this part of the lecture, I have shown you two different ways of doing bulk loading of tuples into a B+ tree. The first one is to do multiple insertion. We'll insert one tuple at a time into the B+ tree, which is definitely going to be slow because of all the poor cache efficiency aspects. And also, the leaf pages will also end up in a random order because of the way that we insert these tuples in a random way. The second option that I described make use of an external sorting algorithm to first sort the tuples to be inserted. And doing so will end up having fewer IOs that is required during the build process, just because of the fact that we're able to retain some of the internal pages in memory while we are loading up the leaf pages, for example. Furthermore, the leaf pages that are created as a result of this process is also going to be stored sequentially, and even so, like linked one on between each other as well. And we can also control the fill factor on these pages as we like, because of the fact that we are building out these leaf pages one at a time. We can fill out these leaf pages all the way up to the fill factor that we decided, and we don't have to rely on the order for which these tuples show up in order to satisfy that particular requirement.